on another way to view example 6. We attacked it differently by showing the double implication here, first showing P implies Q, and then showing Q implies P. And now we're looking into another investigation on this one where we're attacking it as a proof by cases situation. It's an interesting view of this. And so right now we're looking into case 1, assume X is even. We have to show P implies Q. And right at that step, I think this is where I'm getting a little bit foggy on what the details would be. How about we run through the details, see where the snacks could be, or see where it just goes right through. And that might be a better way to kind of address that overall question. Does that sound all right so far, Corbin?
Yeah.
Okay, let's give this a try. So we're trying to show P and if only if P, if and only if Q. Sorry to say that too fast. Throwing cases at it. Case 1 would be assuming that X is even. So if we assume X is even, our next overall assumption is that, or consequence is that there's going to exist K in Z such that X equals 2K. Now we'd be over on this direction, show P implies Q. So P is the statement that 11X minus 7 is even. Q is the statement that X is odd. But here, I think this is where I get into a snag. This would be an impossible condition to show, right? Because if we assumed X is even, then we would directly run into a contradiction right at that spot. So we would say P implies Q derives a contradiction that the contradiction X being even on case 1 would be that X is odd, since it can't be both at the same time.
Okay, I kind of see where you're coming from. Maybe I worded it wrong of the show P implies Q. I guess what I'm saying is like if you plugged the 2K into the 11X minus 7 to show the even or odd of the like result, you know what I'm
Yeah,
saying? And
I
then
think
you could
it's
say
something.
since because if X was even, then more than likely from just the how we solved it before, then it would result that um, 11X minus 7 would be odd. And then you do
Let
it the
me
same for odd and show that only odd would result in an even number.
let me see if I can track through that. So we're saying assume X is even. We get the consequence. Oh, let me not make that mistake again. Exists K in Z such that X equals 2K. And then tracking through the next part, we were going to plug X equals 2K into the 11X minus 7.
Yeah.
We would get 11X minus 7 becomes 11, 2K minus 7. Now we have 22K minus 7, which would then become, let's see here, we can make this is starting to sound almost like deja vu, right? 22K maybe minus 8 plus 1, which would result in a 2, 11K minus 4 plus 1. And this would then assert right at that step, 11X minus 7 is odd.
Yeah.
Well, we would have to then view it through the lens of what's going on right up here. When we assumed X is even, you've assumed not Q is true.
Yeah.
And then when we assumed, or excuse me, when we concluded 11X minus 7 is odd, we've concluded that not P is true. And so what this is really is the contrapositive that not Q implies not P altogether. And
Yeah.
so, yeah, that's essentially kind of the argument that we were giving. We try to go P implies Q, saw a difficulty, hit it with a contrapositive, which is what you're saying right here. Assume X is even. In the contrapositive, we show that's true. But then it's logically equivalent to, that's not on this one. It's logically equivalent to the P implies Q statement. Then we just go to case 2, X is odd, and that one would be a direct proof. So yeah, I do agree with you. You could view this under the lens of, think of this as a proof by cases. I absolutely agree with that. Did that kind of answer the heart of the question there from the argument?
Yeah, I think so.
Gotcha. So yeah, that's a great approach on this one as well. It's really kind of similar to what we did here, but it's just a different lens you're viewing it under. On this one, we were attacking it by saying, use the contrapositive, assume X is even, show 11X minus 7 is odd. But from your view, that's just case 1, assume X is even. And then in case 2, when you assume X is odd, you're just going Q implies P, the converse direction. So yeah, that's a totally valid approach. It's a different view, but it's correct. Absolutely. Other questions about all that so far? Okay, well, this is pretty much what we're doing today. So I think this is a great warm-up question. On the proof method we used here, the idea was use the biconditional, P implies Q and Q implies P. And what Corbin was asking about is, can you think of that as a proof by cases? And yes, you absolutely can. That's one of the things that's kind of weird about all these proof techniques is that it's a spectacular display of creativity. And just depending on your point of view, you might have a really great argument that doesn't exactly fit into these other methods, but it's just equally valid. This one can, again, be reviewed under the lens of just a proof by cases kind of problem. And that takes us again to exactly what we're doing today. Pretty much just, I should close that, more of that kind of stuff. Any other questions or comments, folks, so far before we get started? Okay, thanks for starting us off with that question there today, Corbin. And I encourage everyone to start off with a question if you have one. In particular, we're in a pretty rough section for the homework, so I wrote these problems with pretty much the expectation that people are probably going to be asking about them. I'll be very happy to help out. And in the very next section, 4.4, well, we're not doing anything too different, but the idea here is pretty much all the things that we're proving in section 4.3. They're interesting, but not super interesting. The interest here in 4.3 is the proof techniques themselves. So the mathematical facts that we're proving weren't meant to be very deep. They're meant to be not too deep at all, so that we don't have any of the extra mental noise on what's going on with the mathematics, and we can really focus on the proofs themselves. Then section 4.4, we're still looking into the proof techniques, but now we're bringing in some of the other mathematics that we've done so far in this course. We're going to bring in some information about functions, proving we have an injective function. We're going to bring in some information about set theory. How do you prove two sets are equal, really? And how does De Morgan's law work with set theory? How would you prove those statements? So think of 4.4 as having more depths in the mathematical content, but 4.3 being all about the proof techniques. So that's where we're at so far. And at the end of this week, just as another reminder, I'm going to start the work of getting this information filled out, providing the exact coverage on exam 2, writing out the review problems and all that kind of fun stuff. But that takes us right back to here. Our goal is to solve the last remaining problems on these notes, and then take a look at what's going on in the last section, 4.4 for this chapter. Well, this is the problem that we left off on, and we're looking into the proof by contradiction method. On this problem, the proof we were giving was that if x is rational and y is rational, then the sum x plus y is irrational. And that's a hard proof to do directly. Well, if we take the method of proof by contradiction, the idea is, what do we do here? Assume the negation of phi. And this entire statement, P implies Q, is phi itself, that proposition they're talking about. So we also looked at it from this point of view. If you negate P implies Q, then you have this statement. It's logically equivalent to P and not Q. So we assumed P is true. We assumed not Q is true. X plus Y is actually rational. And at that point, we're hunting for a contradiction. If we can find a contradiction, we'll say it occurred by assuming the negation of P implies Q, or specifically, assuming that not Q down here was actually true. So we went off down that road. When we said x plus y is rational, that allowed us to find two values, u and v, to write x plus y as u over v, same for x. We derived a contradiction just by solving for y. That was the part that is irrational. But once you solve for y, we are exhibiting it as an actual fraction. It's rational, directly contradicting our statement that y is rational, or excuse me, irrational. Then we just say in proof by contradiction, the contradiction occurred by assuming x plus y is rational, or not q. And now we must conclude it really is irrational. We have to accept the other consequence. So it's a weird style of proof. And what we're going to try to do is implement it again to show square root of 2 is irrational. First, any questions about the idea of proof by contradiction so far? Okay, well, let's give this a try. Prove square root of 2 is irrational. Well, that just means it cannot be expressed by a fraction. It means its decimal expansion is non-terminating, non-repeating. Some of those facts are useful, but not all of them. We can prove this by contradiction, but you know what? We need one little result. We can prove the result inside of here if we really want to, but then it makes this proof kind of unwieldy. Sometimes when there's other results inside the main proof that you want to give, but you'd rather separate it out, it's called a lemma. Kind of a weird word. This will be our warm-up problem for the day. Sorry, go ahead. Oh, that's terrible. Sorry about that. I didn't even notice that was going on. Let me see if I can correct that. For folks in Zoom, the actual projector is way, way off. Was it that way the whole time? It could have been just weird glitch. Sorry about that. Let me see what they did to this poor computer. Should be set to duplicate here. Let's switch that around. Okay, that's extend. That looks like the right area. Now back to duplicate. And I think that looks right now. Some of the windows look a little bit messed up, but that's the right screen space. Sorry about that weird distraction there. No help doing a lecture when you can't even see what's going on. Just a double check. Yeah, you bet. And let me get these windows back where they were. Usually I try to do a check on the projector behind me before class started, but looks like I just totally forgot today. And fun story, a real story, I've actually taught a class, I think it was 2016, just like this one. And it was about 15 minutes into class before anybody told me that the projector was off. It was everybody just sitting in person watching me go. So I appreciate you mentioning that. That's always a little bit weird. The Windows are not too happy with that resolution change. But I think we're all set now. Sorry for that weird distraction there. Any questions at the moment before we get back into this weird lemma thing? Okay, so the idea of a lemma is, it is a theorem. It's a weird word. Well, the idea here is, if you say lemma, what it means is, it's one of those theorems that you're probably only ever going to really use maybe once, and that's it. It's leveraged against a larger proof. So think of this as a small mathematical, I'll just say math, fact, to be proven. And immediately used in a larger proof. And some textbooks get in the style of writing out loads of lemmas. Basically what they're doing is they're proving a larger fact in small discrete chunks that are easy to digest. And it really makes sense when there's a more complicated thing you want to show or prove or construct. The idea is divide and conquer. That's what lemma here is doing. there's one small mathematical fact inside the square root of 2's irrational proof that we should just square out right away. And it goes like this. If n squared is even, notice that we also have implied a domain. The moment we say it's even, we're talking only about the integers. Then n is even. So it's kind of strange. This weird little mathematical fact, which we're calling a lemma, is critical to the proof down here. It's not clear how, but we can prove this. So this is the small discrete chunk that makes the proof down here a little bit more readable. So let's go proof. This looks like it's just going to be a direct proof for us. We're going to assume the hypothesis, show the conclusion must follow immediately. So let's say assume that n squared is even. Then we can say right away, there will exist an integer k, exists k and z, such that n squared equals 2k. And now that I'm looking at my proof, I'm not sure if I'm too happy with that. Direct proof doesn't seem to be working out for me. I'm thinking if n is even, I would be able to do something with n algebraically. I can't just take a square root here because that may or not be an integer. Depends on what k is. Looks like we need to backtrack on this. But you know, false starts are sometimes part of the process. Let's leave it on paper here just to say something we tried, didn't work out. So if p, n squared is even, implies, that's the n, q, n is even, didn't work out, your immediate go-to ought to be contrapositive. Let's go with that route. Let's instead prove, let's just scratch out that whole line and say proof by contrapositive. Or proof by contraposition. We're going to assume the negation of q and then directly show it implies the negation of p. So the contrapositive is, again, a really nice technique for these kinds of situations. Let's start by just directly saying, assume q is not true. We'll write out specifically, assume n is odd. Now we can go back and say, then there exists k in z such that n equals 2k plus 1. Now this is something that we can now work with because when we go to n squared, we're not doing anything weird like square rooting k, which is not good for us. We can always say k squared is an integer, but we need extra information to say square root of k is an integer. So with this all set up and being odd in that algebraic form, we can now say this means n squared is, take the negation of p, odd, since, and notice how kind of weird this line is. Sometimes when you do read proofs, information is a little bit out of order. I'm just stating right here, n squared is odd. Negation of p, that's the completion of the proof. And you still have to show it. I'm just saying that will happen, and here's the reason why. Since n squared equals, we're squaring this, 2k plus 1 squared. Square of that becomes 4k squared plus 4k plus 1, allowing us to factor 2 from the first two terms, leaving behind 2k squared plus 2k plus 1. Now we're all set up. That we can directly assert as an integer. Doesn't matter what k is. That polynomial in k is an integer no matter what k happened to be. So we can say since that happened and 2k squared plus 2k is an element of the integers z. So that does it, folks. This, by the proof of the contrapositive, shows the ordinary direction p implies q also true, since the contrapositive is logically equivalent to the main direction here. So that's our idea we want to use. If we see an n squared and we assert it's even ever, and our proof for the root of 2 being irrational, we can directly conclude n itself had to have been even. Well, any questions, folks, with that kind of a warm-up problem there before we dive into example 8? Okay, let's give it a try. We need to prove the root of 2 is irrational. And like we mentioned before, a direct proof like of that might take a lot of ingenuity. So we're going to do something that is equally sound, but to some people not as satisfying, because we're going to assume, we're going to prove by assuming the exact contradiction of that statement. It's such a weird proof that it's always a good idea to indicate what you're doing by saying proof by contradiction. And in a certain sense, this is kind of dangerous, right? When you say contrapositive versus contradiction, it's easy for our mind to kind of just make that seem the same. They're radically different. It's very important to keep these two ideas, contrapositive versus contradiction, totally separate in your mind. With a contradiction, if the statement is that root 2 is irrational, we'll say assume to the contrary, root 2 is rational, which means its decimal expansion either terminates or we can find a length for which it starts to repeat infinitely many times. But that information doesn't really help us algebraically. We're going to say rational also means we can express it as a fraction. That gives us the hook algebraically, just like writing down n equals 2k allows us to do something with algebra to make a conclusion. And we say assume to the contrary just to alert whoever reads this, that's where the contradiction is going to come up. And if we find a contradiction, it's because of that assumption here. We'll negate it again, concluding overall, root 2 had to have been irrational in the first place. So here's how it starts. We're assuming the root 2 is rational, so we can now say immediately, then there exists A in Z, there exists B in Z, but we want B to be non-negative. One approach is just to say greater than 0. That still allows us to have negative values since A can be any integer. And then the last statement, root 2 is rational, just means square root of 2 equals A divided by B. So again, that definition of being rational gave us something to work with algebraically. And that's what we're going to do next. Do something to this, because there's a contradiction living inside of that. We just have to find it. Any questions at all, folks, on just the getting started steps? Okay. Well, we have an equation. We're great at algebra, but we need to know what we're going for. Maybe a good start is, let's just solve for A. Let's work with that value there. We'll say next, A equals the square root of 2 times B. So that's a new equation. This equation is true based off the truth of this equation. And then it implies really just a long stack of implications now. Well, what should we do to this? We could square it, and then we've eliminated root 2 from the problem entirely. Kind of weird. That's the object of interest, right? But if you square it, at least we have a little bit more we can do algebraically. Let's write out A squared equals 2 B squared. There's another implication that happens just through this equation. So let's focus on this, study this, because we need to make a claim about A squared. Anyone see what the claim should be on A squared based off this algebra?
It's even.
Absolutely. That 2 right there was the whole thing that directed us to that. Good call. A squared is even. It's weird to put an exclamation mark, but that's an important statement right there. That's the tie-in. Just because we saw a 2 there we can now say a squared is even, tying in the lemma above. If n squared is even, or a squared is even, or anything, we can immediately conclude by the lemma, a is even as well. So we'll say down here, by the above lemma, this means a is even. Now that we have that, we have even in the numerator. But we might want to make one extra assumption here. Let's make it right here and now. We know that a is even. What about b? It could be even as well, and then you would just reduce the fraction, right? But when you found the a and b for which root 2 equals a over b, we can now make another really strong assertion. Here's how it goes. Without a loss of generality, this is like a big buzzword whenever proofs are going on. It's kind of like saying proof by contradiction. It's alerting you something is about to happen. And when you say without a loss of generality, something interesting is about to happen as well. Well, there is really cases here. And when we say without a loss of generality, what we're also asserting is that one of those cases is so simple as to not even really needing to be rolled into it. Here's what the without a loss of generality assumption is. We may assume A, comma B have no common factors. And why is that? Well, it either does or it doesn't, right? In case one, if it does have a common factor, whatever it is, we would say eliminate that common factor, get A1 and B1, and assert now they have no common factors, and keep on doing that. Or in case two, they just have no common factors, and that's just the proof we're about to give. So in either case we look into this, we're giving the same exact proof. But we still have to justify that without a loss of generality. The extra justification would be if A, B have common factors, reduce A over B to A1 over B1 and apply the entire argument to root 2 equals A1 divided by B1, coming from that algebraic form right there. So this is a statement in the middle where now that we found A is even, if we find B is even as well, that's the contradiction. Because with this statement here, it is okay to assume the moment we wrote A over B, they had no common factors in the very first place. And even if they did, restart the argument with A1 over B1, reducing the fraction. Root 2 is still equal to that reduced fraction. And then we still have no common factors. That's what we mean by without a loss of generality, that statement in the middle. Does that make sense to folks so far?
Could you like specify that A and B have no factors in the statement up top right there? Yeah, right
Yeah,
there.
absolutely. And that would have been the better thing to do. Absolutely. What happened with me was I just totally forgot. I got that A is even. I realized B is going to be even. And then I realized, oh, doesn't help us unless we make this strong assertion. So yeah, I totally agree with that. This really should have been right here before we even got into that statement there. But I felt like just switching it around out of nowhere might have been a little bit weird. Apologies to everyone working a pen. But yeah, I agree with that. Let's actually just switch it officially on the notes to make it flow better. Other questions at the moment? Okay, so now that we have A over B, it would have been nice to remember that in the first place. But with a little bit of a trick with digital ink, we'll pretend we had those thoughts all along. We now said, after taking that algebraic form, Doing some algebra, a squared is even. By the work above in that lemma, a is now even. And that means the following. Next. Well, let's work with this. If a is even, that means, once again, there exists k in z. There's some integer k such that a equals 2k. So we have now another big part of this, a equals 2k. Where can we throw that? Well, you could throw that right here. Just plug it in for a squared. So this equation right here, we can now reuse. First, let me make sure I have enough space to finalize this. Okay, we're going to reuse this equation, derive our contradiction at this step. So we said next, there exists a k such that a is equal to 2k. Therefore, a squared equals 2b squared implies, let me match up that color coding. Two k squared equals 2b squared. Then that implies over here we have 4k squared equals to 2b squared. A little bit more algebra, we can divide, solving for b squared. This implies b squared equals to k squared. But there's that 2 again. We like seeing it because now this is telling us b squared itself is even. Let's make that assertion. This means b squared is even. And we've already said before, by the above lemma, that would imply b itself is even. So let's just say it as a quick statement here. This implies b is even by the lemma. Well, we have two things now. A is even, b is even, but being even just means you can divide by 2. It's equal to 2 times something. So if that's the case, we've also have this problem. Everything highlighted in yellow is now a direct contradiction. You cannot assert A and B have no common factors, deduce A is even, deduce B is even at the same time, because now the common factor is 2. We get to state we have found a contradiction. This contradicts let me zoom out just a touch. The assertion A, B have no common factors. Let's justify that a little bit further. Since A, B both even means they have a common factor of 2. This is a longer sentence than I thought it would be, but we got there. And we're still not done. Let me zoom out just a little bit more. Okay, so with our full view of the argument, minus the lemma above, we found that we have a contradiction. Altogether, justification of the contradictions here in the purple statement. And now we want to say what led to the contradiction. Really, we kind of indicated that's right at the top of the proof when we said, assume to the contrary, root 2 is irrational. We just wanted the reader to know immediately what led to the contradiction so that we can negate this statement as well. Negation of this statement is just saying root 2, now we know to be irrational, the overall argument we were trying to give. We just need to say all that. So let's say here, this contradiction emerged from the assumption Root 2 is rational. And we're now done. Therefore, root 2, let's say it a very strong way, it must, always very, very strong word in mathematics when you say must, it must be irrational. Just no way to get out of it. And that's one of the more classic proof by contradiction type problems out there. It's nasty, it's long, convoluted, but it forces you to really look into what is a proof by contradiction, how to find the contradiction, how to escape a proof by cases. Lots going on this one. It'd be a horrible exam question, but you know what? This could potentially be maybe an extra credit question on the final exam, something along those lines. Any last questions at all, folks, on getting through the entire sketch of this one?
I think you might have meant to highlight in yellow that A and B have no common factors.
Yeah, well, how'd that happen? Thanks for spotting that. No common factors is the intention. I think I said it, but I never wrote it. That's a huge fix. Have deserves a different color there. Let's really highlight the main assertion.
You wrote it right in the sentence before.
Oh, I gotcha. So yeah, it just had to be duplicated there. But you know, if it's highlighted here, then it's like we missed the correct statement entirely. We're just reading it wrong all the time. Thanks for that fix there. Any other questions or comments or weird oddities to fix? Okay, well, we did it, folks. This is kind of a nasty proof. And weird side thought on this. Back in the day, we had a philosophy professor that taught on this campus, sometimes on the Pocatello campus, named Mr. McCurdy. He passed away during the COVID years. But in his intro to philosophy class, this was a problem that he actually assigned students. Whether or not you had mathematical background, he thought, we're working on logic, you should know how to do this. Pretty brutal problem, I would imagine. But at least we have a little bit more tools of the trade to help us really see the whole argument. But now, here's the last one. We talked about these a little bit before, counterexamples and disproving a claim through a counterexample. The idea is counterexamples come in whenever we have a universal quantifier. If we say for all x and s, p of x is a particular element, or hang on, let me reread my statement. A counterexample to this claim, for all x and s, p of x, the predicate, is true, is just one element in the set S that makes the actual predicate false. That's kind of nice. What it does is it totally disproves the claim for all x and s, p of x. One example that shows p of x evaluates to false as a predicate is your disproof by counterexample, which is a weird statement because if you negate this, it's true. It'd be a way to prove the existential is true by finding a counterexample to the negated statement up here. So even though it's called a disproof, it really is a kind of proof in a real sense. And I don't really have too much to go on this one, but I felt like we should do at least one problem, and here's that problem. And now I feel really bad about the homework because the one we're doing here on the notes is not too bad. The one in the homework is actually really hard, so I feel like we should just give a hint to that one right away. Last homework assignment, section 4.3, or the last problem on that homework 4.3 section says, disprove the following statement. For every integer n that is non-negative, the integer n squared plus n plus 41 is prime. And you know what? That's turned into a pretty nasty problem. It's not because it's a true statement. There's no way you can write down a polynomial that just generates primes. That's going to evaluate to non-prime eventually. But my hint on this one is, I think you need to be above 39 to find the very first counterexample. So you have to go pretty high. Start looking in the 40s, and that's going to save everyone tons and tons of time, I think. So apologies for this one. It was nastier than I thought it would be. It was meant to be more like this one. So let's give this one a try. We don't have to go up into the 40s for the first counterexample. But it says for every integer n, 2 to the power of n plus 1 is prime. This is an important classification of primes. This is called the Mersenne primes. And there's an interesting collaborative computational project where people are looking for these all the time. So for our claim, though, it's not true that these are always prime. Sometimes they're composite. People just use this as a way for looking for arbitrarily very, very large problem numbers. So this is what our disproof is going to look like. First, we just do some scratch work. Set n equal to, well, it says for every integer n, but the only way we're going to get integers out of this is if we stay away from the negative integers. So we can throw in a 0, though. We just can't throw in -1 because then we would get 1.5, a non-integer, and that doesn't match up with primality. So start at n equals 0. This whole statement is the predicate, 2n plus 1 is prime, but it would become 2 to the power plus 1, to the power of 0 plus 1, 1 plus 1 is prime. And it's true. So that means we don't have a counterexample, but it really is false. It doesn't work for every integer n. We just have to find the integer where it fails. So now we go into a computational kind of problem. You can imagine developing an algorithm, maybe a for loop that halts at the first prime, that does this kind of check for you, but we're doing it by hand. So at n equals 1, we're going 2 power 1 plus 1. That's just 3, and the statement would be 3 is prime. True again, so we keep going. Kind of methodical work. N equals 2 next. Here, that will be 2 power 2 plus 1. We're on the next prime number, 5 is prime. So true, and then update to the next integer. I don't know where the counterexample would be. I do not necessarily want to throw in something like 71. I mean, it could work. We could just luckily guess a wild number, do 2 power to 71 plus 1 and computationally check if it's prime or not. It's already a pretty big problem. So we're starting off with the lower integers. So at n equals 3, 2 power 3 plus 1 becomes 8 plus 1, which is 9, is prime. But that statement probably hurt to write in, right? It's absolutely false, which means we have found a counterexample. We can now say the disproof goes at n equals 3, 2n plus 1, let me fix the plus 1 there, is composite. This disproves the original claim. And we're done. That's kind of a fun little proof. It's also a little bit alarming in the sense that there's no real creativity or intuition here. This is really just straight up brute force computation until the counterexample comes up. So again, on the homework problem here, start around 39 and start going up, and that will save you potentially a lot of time on that one. Well, I think that's all we really have to say on these notes so far. Any last questions at all, folks, on getting through these 9 different problems? Okay, let me make sure this actually saves before I move on. Occasionally, Microsoft just gets really upset, I think, when the document gets long. There we go. I think we can close that out. We get a mental break. That's a good way to look at it. It may take a bit longer to exit. We don't want that then. I closed out that whole thing. There we go. And now we're into section 4.4, nearly done with chapter 4. After that, we'll be looking into other interesting applications throughout the textbook. But this is our opportunity to look into just a couple more proofs. Not stuff talking about so-and-so is even and something else is odd, or things along the lines of something or something is an integer when something or something is irrational. We're looking into maybe more interesting mathematical facts. This one's kind of a warm-up problem, but it is interesting. We talked about bijections. Now this is our opportunity to say something is a bijection by really proving it. So it's a short set of notes, but the next problem is going to be, it might view a little bit more difficult. This will be now a look into set theory a little bit closer. We have the core definition 2.27 in chapter 2 saying sets are equal, denoted A equals B, if A and B have exactly the same elements. It's a good working definition, but actually with set equality, this is the way we really use and verify set equality. Two sets are equal if A is a subset of one and B is a subset of the other. That's kind of weird, but if you think about it, it ought to be true. And it is, we'll prove it. But maybe the bigger proof, or the bigger example that we're going to get into is going back to this table of logically equivalent propositions. That's kind of going back to a comment that we made earlier, that a lot of this stuff dealing with propositional logic is no different than set theory. It's kind of weird. Take, for instance, De Morgan's laws for logic. De Morgan's laws are either stated in a logic section like this, or they're stated in a set theory section, and there is literally no difference at all. Take a look at this statement. The tilde is just for the complement, matching up with the negation there. Union is matching up with or, and it becomes the complement of A intersect the complement of B. Analogously, not P and, so union flips and or also flips, not Q. In fact, all of these properties, except for the ones with, say, the exclusive or, for example, all of these properties right here can in some way be reconvened as a set theory property. So that's the next little bit that we'll be looking into, just connecting some of the information that we gathered with some of the information that we started with, is the idea with 4.4. Well, let's see, I think we have time to get through a couple of these. We'll start with going back to functions. Any questions first at all, folks, before we begin in earnest with these notes? Okay, well, let's begin. The review of being onto, one-to-one, and a bijection is contained here. But we also have kind of a different view of all this kind of stuff. Let's see if we can redefine these in a way, just onto and one-to-one, that might be slightly more helpful for doing a proof right here. So onto says, for every B and B, let's just start with there. Onto, we quantify this, we can say, for all B and B, there exists, so throw in the existential quantifier, exists X, let's match up what they said, exists A in A, such that f of A equals B. So if we can really target this definition, we'll know we have dealt with onto. We're trying to show that the function is a bijection, so we're showing it's onto and one-to-one all at the same time. So two elements to this proof. And then finally, one-to-one, this one's a little bit more tricky. This might be a homework question, but let's do it anyways. We need this, it's good information for us. Function f is called one-to-one if for any b and b, there's at most one a and a, such that f of a equals b. There's a lot of ways to write this one out. But sometimes with one-to-one, a different view you can take is, take this whole statement right here, instead of saying for any b and b, let's focus on at most one a in a. So we're focusing on f of a, or go that route. And the at most of one here can now be rewritten as, let's see, if f of a1 equals f of a2, let me fix some penmanship there, then that will imply a1 equals a2. So this is 1, 2, 1. maybe let's pause on this one right here and see if we believe it in the first place. They said that there's at most one in A such that F maps A to B. And I'm saying it slightly differently. I'm suppressing the B here and just saying, suppose F maps A1 to something and maps A2 to the same thing. So B comes up twice, we just never said it. Now I'm saying if F takes A1 and A2 maps it to the same element through this equality here, well, there's only at most one that can map in that way. So the inputs A1, A2 must be identical. I think if we're going to prove with one-to-one, this is the easier statement it actually turns out to be. But let me ask the class, how do you folks feel about this statement? Does that make sense for one-to-one? Okay, well, with those tools in mind, let's work on this function right here. It's absolutely a bijection. You can really tell just by plotting it. It would go like this. The plot of x cubed passes a horizontal line test, which means it's an invertible function, which automatically then means if it's invertible, it is both one-to-one, it's on two, it's a bijection. But we're going to erase all of this, ignore the geometric approach, because you lose that geometric approach the moment your function goes like this. And these functions are just as important. These would be the linear functions in linear algebra, potentially. And them being one-to-one or onto, equally important as well. Definitions here don't care about the sets. And so we're going to pretend that it's a pretty tough set as well, like R2 or worse, and do this just purely logically through the definitions. That way, whatever work we do right here, it carries over to the more complicated setting, like the linear algebra, or if this was a nonlinear function, a calculus 3 type of function, for example, our work here still carries over. It's more about the idea, not necessarily about the view of this smaller kind of function that we're dealing with. So we break this off into two statements. And just to alert, if you're rereading the work you did, it's good to say here how this is going to flow by saying first, show F is either one you want, but let's just go in order. It makes sense. Let's show on two, and then we'll do one-to-one. First, show F is on two. Okay, they're really both quantified statements. I didn't quantify this one, but here with the on two one, I think it's good to really start with that right there. We want an arbitrary element B in B. Because this is a universal quantifier for all, you can't pick a specific one. This has to be totally arbitrary. We'll even say that right here. Let B in R, we're thinking about the codomain here, be arbitrary. Okay, so now that we have that, we have to find an A in A, that's R the domain, such that F maps A to B. Okay, so let's put this all together. Write out, if B in R is arbitrary, then F of A equals B. Writing down this equation is our attempt to find that A. It's got to be a real number. Only way it's a non-real number is if we can't even solve this equation at all. So let's see if it's even solvable. First step we take is we unpack the function notation, use this, and put in A cubed. So now A cubed is B, and if A cubed is B, we're just back into ordinary algebra. This would imply A equals cube root of B. So this particular A is the A that would exist in the domain for which F maps A to B. And we did it in kind of a roundabout way. We started with the function, we showed algebraically that these steps work, but you know, another thing that's really tricky about these kind of proofs is my arrows go one way. They have to reverse to make this entirely logically sound. And so let's see if we can justify that. If you were at this equation, you could cube both sides and return to this one. So it really is a biconditional situation. One equation can apply the other. And keep in mind that doesn't always work. For example, if you're doing, say, how about x squared equals, maybe it's something like 9. If you take the square root, you get x is 3 or -3. No, you could reverse that. Then you could reverse to get back to x squared is 9. Trying to think of an equation that wouldn't be easy to reverse the steps on. Maybe I should have come prepared with that one. I might have to come back to that concept. But let's see here if we can still reverse this. If we say a cubed is b, a cubed itself takes on the form of something cubed, which is the mapping. So that means it does really reverse in this direction as well. So because all of this is reversible, we went in the forward direction, found a. We observed it can also go in the backward direction to show f maps a to b, our target up here. We've got it. We can now say, then that happens, and this shows f is on 2. Because we have found for arbitrary domain element, we call it b, the exact and correct, let me start over. For an arbitrary codomain element b, coming from the codomain over here, we found a domain element a, coming from the domain here r. It's confusing, they're both the same, such that f really did map that one value to the arbitrary element b. So we've established onto, we now move over to one-to-one. But does that make sense to folks so far on the onto argument? Okay, let's attack one-to-one then. So let's say next, we show f is 1-to-1, or injective if you prefer. So essence of 1-to-1 is we grab these arbitrary elements with the intention, and we want to show that they're equal, but we allow them to be arbitrary to start, and we want to conclude equality. So let's begin by saying, let A1, A2 in R, it might be helpful for here just to say domain is what we're thinking about when we said A1, A2 in R. And when we said B and R over here, we were thinking codomain. That might be good just to organize our thoughts on where things are coming from. So let A1, A2 be arbitrary domain elements and assume we're assuming the hypothesis of the if P then Q part of the statement. Assume f of A1 equals f of A2. So we've made that assumption for those two elements right here. If we can conclude those domain elements are in fact equal, then we have found the essence of there's at most one A and A that maps to a particular value, the one-to-oneness. So we have an equation here. We have a function that we can now re-express through that equation. So we can say this implies where it was f of A1, we now have A1 cubed. Right-hand side f of A2 becomes, just past it to the function way over here, we have A2 cubed. And we're not as concerned about the bi-direction of the arrows. We just need to go one way because we're going one way up here on this logic. We just want to show A1 is A2. And that'll totally work. Take the cube root of both sides. And this will imply A1 equals A2 as required. Keep in mind, if this was x squared, we do have a big problem. You can't take the square root and imply A1 is A2. A1 would be plus or minus A2. Huge logical problem. But that's because with an even power, it's not a bijection any longer. So the logic breaks down at that step. Here, getting the A1 equals A2, this implies, let me say it differently. And so F is 1-to-1. So we've made two conclusions. F is on 2, F is 1 to 1. And now we have to make the final conclusion, back to definition 2.53. We showed that F is a bijection. So let's make that our overall conclusion with those two parts verified. Therefore, F is a bijection. And we got it, folks. That's another look into dealing with functions, one-to-one and on-to-ness. Now that we know it's a bijection, an interesting statement here is that you don't have to call it the codomain any longer. R over here is now the exact range at the same time. But it'd be weird to change the statement here. We had to think about it as a codomain until we proved that fact down below. But any last questions at all, folks, going through this argument? Okay, let's see if we can get through one last one, and then we'll call it a day officially for the week. So here's the last one. Again, this one is an interesting fact on its own, a very, very useful fact in set theory. And sets, they come up all the time. I've been mentioning linear algebra, but if you do take linear algebra, you get into a concept called a vector space. And the very first thing they say is a vector space is a non-empty set, and then loads and loads of axioms, information about it. So proving things about sets is extremely relevant. It's going to come up in just about any class, depending on how much they want you to prove in that class. And so now this fact is tremendously useful to us. The major use of that theorem is going to be when we use it to prove this statement here. That's a statement about set equality. So we need a clean and easy way to actually prove that these sets really are equal in the first place. And it's through this theorem above. So this is the other half of the notes where we're just looking into a little bit more review, a little bit more of extension of our knowledge on set theory. It says two sets A and B are equal if and only if. So we have a biconditional statement. A is a subset of B and B is a subset of A. Lots to say on this one, but let's go with the forward statement. What I mean by that is we have a statement here. A, B are equal is the statement P, if and only if. This is a big compound statement, but I'm going to call it overall a statement Q. And because of the if and only if, we have to prove two different directions. First, we'll prove the forward direction, assume, and let's actually organize a little bit better. Let's say first, assume A, B are equal. And our goal is to show that statement there. Not a bad idea to just say your intention. When the proofs get a little bit longer, a little bit more complicated, when there's other pretty decently heavy mathematical facts causing mental noise, just saying what you want to do is really powerful. In fact, in computer science, this is a really embarrassing method, but it's real. There's a way of looking into your code to determine if it's wrong. It's called rubber ducky decoding. What you do is you place an object, maybe a literal rubber ducky, you tell that duck exactly what your problem is, where the hiccup is in your code. And in that whole process of just saying what your problem is, even to an inanimate object, allows your subconscious to think about that problem, see it from different angles. And a lot of times people have a moment of inspiration. They stop talking to their duck, they fix their code. It's kind of what we're doing in essence here. We're going to assume A and B are equal. Then just tell yourself what you want to do next. We must show A is a subset of B. Kind of just depending on how to try to determine how I want to write it. Using a little bit more of logic, I'll say, and B is a subset of A. Subset equals, but I'll just say subset to save a little oxygen each time it comes up. So that's how we're going to start it off. Assume A and B are equal. Try to make that conclusion. So next step, we say, since A and B are equal, That means they have exactly the same elements. So let's start from that position. We're trying to show subset relations. So we can say this. Let X be an element of A. Because we assumed A and B are equal, we can go back over here and say, then X is an element of B. That's just set equality. They have to have the same exact elements. But now the subset relation comes in. You have a subset if for every element in the set A, it's also an element of the set B. And that's what we said. We didn't say what X was. It's totally arbitrary. So we can now say next. Then A is a subset of B. That's part of it. And now we can just turn it all around. If we want to show that part, we can say next, let X be an element of B. Go back over here. We said A and B are equal. That means A also contains X. They have the same elements. So we'll say, then X is an element of A. But if you grabbed an arbitrary element of B and you're able to say that arbitrary element is also an A, that's the other subset relation. So we go and say, therefore, B is a subset of A. And we've done it. We've shown this holds, and at the same time, the other end holds. And so this completes this half. Well, it's kind of a weird proof, but we're getting there so far. Any questions at all, folks, on the first direction, P implies Q? Okay, now if we can reverse it, assume Q is true, derive that P is true, we have a powerful tool to derive set equality. And again, the only way we're really using this is in the larger proof. We don't have time for today, it looks like, but we'll come back to this one on next Tuesday's class. So now here's the backwards direction. Next, assume this statement. A is a subset of B, and B is a subset of A. We must show A equals B. So that has to be our conclusion. But how can we do that? Well, this whole proof, when you really look at it, it just seems like it's a different rewording of this whole definition. So let's follow that to the letter. If we want to show A is equal to B, that means we're just showing A and B have exactly the same elements. Let's start by going through this assumption right here. When we made that assumption, we can now say, since A is a subset of B, all elements X and A are also in B. And really all I did here is say exactly what it means to be a subset. Pick X and A, it has to also be in B. Well, that means B contains all of the elements of A. And then we could just reverse and go to this other side. Since B is a subset of A, all elements X in B are also in A. And now if we take these statements together, every element in A is also in B, but at the same time, because of the end there, every element of B is also in A. That's just a long and convoluted way of saying, since A and B have exactly the same elements. So that's our conclusion. This implies A equals B, since they have the same elements. That completes a proof. And again, it's weird because when you really look at this, it may not feel like it really has a whole lot of value to it. It felt like we were just taking that definition, slightly rewording it. But it's a lot more powerful than it looks like. Because if you can split up a statement of set equality, A equals B, into two statements here that you prove, oftentimes this is the easier way to break up the problem. Trying to show simultaneously that every element in here is also in here all at once is actually a pretty enormous undertaking. The logic gets really fuzzy and convoluted all at once, but it's the same idea as before, just like proof by cases. If you can break this up into two statements, divide and conquer, everything comes out cleanly, the proof becomes readable, and if it's readable, you're able to convince yourself. That's all we're trying to do with proofs, write down a convincing argument. And if you can't convince yourself, then we're kind of stuck in the mud at that point. So even though it seems like a silly mathematical fact that's a rewording, it's a true and powerful statement. But before you can use that statement, it really has to be proved some way, shape, or form. And that's our proof down below. Next class on Tuesday, we'll use that to prove the larger example down below. Or thank you, yeah, on Monday. I keep forgetting what days we meet. But with that correction, next time we meet on Monday, we'll finish off these notes, move into the next chapter. Any last questions at all, folks, so far?
Can I ask one question?
Yeah, go ahead.
Till now, we're dealing with proving or disproving, like proposition and negating. Is there any mathematical philosophy that deals with with synthesis? Like we're dealing with thesis and antithesis, and then combining thesis and antithesis to a synthesis?
Let me read out that statement. That's a great question. Do we have mathematical properties for, and how did that statement go again?
Synthesis, that is the fusion of thesis and antithesis.
You know, my honest answer to that is I'm not too sure. I'm gonna have to really break down these words and take a really close look at this one. This looks like it's going to be a question I may have to come back to you on this for sure. Very interesting question. So this was, synthesis, fusion of thesis and antithesis. Yeah, I'm not too sure on that one, but you know what? That's a good project for me. I'll have to come back to you on this one next time we meet on Monday's class. Let me save this here. Call this a reminder. And again, I'm not too sure on that one. That's a really great question. I'll have to come back to you on Monday, and I'll start off class with getting right back into that one. Sorry, don't have any real knowledge to really give you an honest answer in the direction of that question there, but it's a great question. We'll spend some time on it next class.
Sorry, it's a weird question, but like.
Sometimes those are the funnest ones though, right? So I appreciate it as well.
So, and I've got another question.
Sure.
So what if if there is not one exact truth and there is a probability of truth? What if we're dealing with probabilities? Does this
dealing with what did you say?
Probabilities, like if you're not certain of certain truth, like if there is a probability of a truth, in that case, do you have does this law holds in that case as well, or like?
It depends on the statement. Let me see if I can read this out for the second question. Let me know if I've missed the question. In situations where we know the probability that, say, a predicate function p of x is true, what mathematical tools do we have for a proof? Is that the essence of the question there?
All right.
I would say, yes, we do. If probability is coming into the problem for a predicate function, then it's going to depend on what the overall statement is about. But the overall statement itself is probably a statement of probabilities in the first place, in which probability theory has loads of theorems, mathematical facts that can be leveraged against this kind of a question. But yeah, I'd say for this one, my honest answer is yes, probability theory itself would directly attack those kinds of questions.
Got it. So I'm dealing with machine learning, and then like it does not project one concrete value. It gives you a probability distribution as a final outcome. So
All probability distribution, as in some kind of t distribution, some normal or exponential distributions are what you're getting.
right.
Gotcha. Yeah, for that machine learning context with probability distributions, if you're dealing with proofs involving probability of a predicate statement, you just have to use other mathematical facts about probability itself in the leverage of that problem. There is what I believe would be going on in that kind of situation.
Sure.
Well, I'm definitely going to take a look into this question up here as well. And I'll keep that as a big reminder here on the notes on that document to start off class with this one here.
So that might be a that might be a silly question, because I was thinking from the perspective of philosophy. So we have this Hegelian dialect that deals with thesis, antithesis, and the combination of that results synthesis. So
Gotcha. Let me add that to this from philosophy. And you know what? Because it's a philosophy question means it's an even better question, because everything we do in logic, I mean, that is under the purview of philosophy in a very, very real sense. So yeah, I think gives it a lot of extra context to help out, give a good answer to that question there. Well, any other questions, folks, before I turn over to the next class? Okay, well, have a great evening, everyone. Thanks for the participation. Excellent questions and good eyes on finding those weird little mistakes in the proofs. Take care, folks, and we'll see you all next week.